Next speaker is Steve Pederson, Black Ochre Data Labs, Telethon Kids Institute, and he's going to tell us about some snacking we can be doing by Asia. And there's some very cool stickers you can pick up in this package up the back. So I encourage you to do so. Welcome, Steve.
Hi. Thanks, everyone. Can you hear me okay? If I leave my mask on, I'd prefer to do so. Cool. I'm Stephen Pederson, as Matt has indicated. My preferred nickname is Stevie. I have an internet presence as Steve, but as I'm currently emerging as non-binary, I'm switching that gradually over to Stevie, and I'm very appreciative of my current colleagues for helping me with being so supportive and kind in that move. Yes, okay. So I'm a postdoctoral bioinformatician at the Black Ochre Data Labs. We're based in South Australia, which are the traditional lands of the Kaurna people. I'm also a little bit, hopefully a few of you have used my package NGS reports, which is about parsing FastQC, star, max2, log files into R. And if you have a favorite tool that I haven't written a parser for, please hit me up. I get really excited when people use my packages. So, yeah, please hit me up if there's something you'd like it to do. So prior to my joining Black Ochre Data Labs, I worked for a couple of years in breast cancer research in the Dame Roma Mitchell Cancer Research Laboratories. And they were very interested in how transcription factors are working together, in particular the androgen receptor, estrogen receptor, and another cofactor, GATA3, and how they were responding to DHT treatment as a potential therapy, or basically activation of the androgen receptor as a potential therapeutic for breast cancer. So my job was very much to look at multiple breast cancer models and see how they were behaving, and looking across the different models to integrate the results across. So I ended up building a workflow which I call GRAVI because I love terrible jokes. So I came up with a name for it. And the idea behind this workflow was I needed a way of producing output where I was confident in the results and I could work at the higher level, but also the results produced by each individual analysis would be, of a high quality to stand alone. So I wrote that workflow as a state-make workflow, and as implied by the name, you can put in variable inputs. I was very much inspired by the workflow package, but I made a few changes to compile aspects in parallel, which you can't do in workflow. So here's what the output of GRAVI looks like, a bit of a screenshot. It looks very much like workflow output. The header at the top, I can't remember the name, but the index bar, it's automatically generated from your inputs. So in terms of the GRAVI workflow, the minimal data it can take is one chip target with 2 treatments. It's about differential binding and looking at the way chip targets are responding to treatment. It really comes into its own when you combine multiple chip targets across 2 or 3 conditions, because then you can look at how they're moving together, and it does that as part of the workflow. So I built extraChIPs really as key infrastructure to help me build that workflow. So it really is just a series of utility functions. I hope I haven't reinvented the wheel that other packages have done, but I find some of the functionality that I came up with to be quite useful. And so I thought I'd show it off to a few of you guys, and hopefully you find it useful too. Okay, so the function that I use the most is just simple tibble conversion from a GRanges to a tibble. You can do it these days. I tried it just in base R without loading the package the other day, and it does convert nicely, well, far better now than it used. But the way I've implemented this, if you start with a GRanges object, sorry, I've got excited with my new Quattro format there. basically puts the range as a character vector column, which I find far more useful than having those individual columns. It handles any of the compressed S4 list columns really nicely, just by using the vectors package, which came out of RStudio. And then you can simply coerce back from a tibble to a GRanges object just by telling it what column the range is in. You can also use that function if you've got a GRanges object with ranges in another column. You can just substitute the ranges across very easily. So I find those functions particularly useful. And some of the other issues that I came across while I was building the other workflow, well, when you do a lot of the kind of the reduce or those types of operations on a set of ranges, you often lose, well, you always lose what's in the mcols side of a GRanges object. So here's an example, GRanges, it's some of the transcripts from CTLA4. And if you just do reduce on that, you get back a single range. But I've introduced a suite of functions with MC at the end. And so reduce MC gives you back the same range, but with the mcols information retained. If it's a simple character vector, like in the gene name, it comes back as a character vector. But if it needs to be compressed into a list, it will do that as well. There is a small cost overhead in terms of computational speed, but I still find that very useful. A more real-world example of what you might like to use that for is if you've got a series of transcripts, you want to find the TSS for all of the transcripts. You could do something like this, grab the range, set the width to be 1, and then run reduce MC, and you'll have the TSS for each of the transcripts, and you'll know which one goes with which. It just saves a bit of time. So I've put together a whole lot of those functions which keep the mcols information. So setdiff, I've got the equivalent, same with union and intersect. The way I've written it, you only retain the mcols from the query range. So if you're then looking across two ranges, it's the query range you can retain. A couple of tidyverse inspired functions like chop MC, again, where if you can see the ranges for 3 and 4, or transcripts 204, 203 are actually the same range. So you can just do a quick chop to reduce things down, or you can do a distinct like in the tidyverse. But that way it won't chop, it'll only keep the first one. So you could rank by p-value or whatever you want. I've got another function in there for stitching ranges. And you find this one really useful to set up for looking for super enhancers, where you can stitch together H3K27AC marks, but you can put clear barriers saying do not join across this range, which I think is, again, quite useful for that particular context. So that was some of the just range manipulation strategies I've gone for. But clearly, if you're working with ChIP-seq, you often want to work with peaks. And so I've got a few functions for handling that. When you're importing peaks, reality is they're going to have the same format. So I tend to import them just straight as a GRanges list from one set of files. And here's what they come out with as a GRanges list. Can I scroll down? So that kind of makes import a little bit easier for my way of working. Then there's some standard functions. I've only imported 10 peaks from 2 samples here, but you can just plot the overlaps very quickly and easily. I've changed the names of them here to make them plot nicer. I'll drop the narrow peak suffix. I hope you don't mind. You can also plot the overlaps as an upset plot, retaining perhaps the score column, so you can see how the score tracks with peaks that are represented across multiple replicates. Ooh, how's that on that screen? Too small? Damn it, I was trying to fit more on one slide. So it makes life easy again for trying to get a consensus sequence. If you put in a GRanges list, just make a consensus and you'll get back a true false column for which replicate the peak was in, and then the final column tells you how many peaks, how many samples have an overlap with that consensus peak. Again, I just found that convenient. You can also retain one or more columns from each of the replicates. So you might want to retain the score column from the replicates, or do something even fancier where you get the estimated center of the peak from the narrow peak file, and then you can take the median of that across all of your replicates and just get an approximation of the center. So then you could do like a diff bind style analysis, but without having to use their architecture. I've also implemented something for helping you map to features, which a lot of people have done before, but I've introduced a function called best overlap, where you just stick it, see what feature overlaps at best. So here I've figured out which of those peaks maps a promoter or an enhancer or nothing. And then you make a little pie chart. I'm bringing back the pie chart. And it's just a ggplot object. So the workflow that I was actually working with, as I developed this package, I kind of came up with my own strategy for looking at differential binding. I was using a sliding windows approach, as Gordon and Aaron have advocated for with the Seesaw package. But the filtering strategy that I implemented, you can combine the signal to input threshold and the overall signal, and you can provide regions which you go, here is where I think the signal is likely to be, and it will set the threshold from that. And in the GRAVI workflow, this was what I went with at the time. I may revise this, but my approach for differential binding was to use smooth quantile normalization on the log CPM values, followed by limit trend, followed by the treat method for detecting differentially bound regions. And so everything is based around working with that approach. So I then had a few plotting functions, and because I was dealing with the androgen receptor, which is cytoplasmic shifting to nuclear, you don't have even signal in two treatment groups. So here's just one of my plotting functions showing the log CPM values before and after normalization. You can use, because everything comes as a summarized experiment, you can plot the RLE straight from your summarized experiment, PCAs as well. I'm running out of time, so I thought I'd get as far as I could in my little window. The way I was working with the differential binding was I was grabbing the window with the most signal before you merge them across the region, and I thought it made sense to grab the window with the strongest signal. So I've got a little function which just wraps multiple steps from Seesaw. So here's my pretend results from a tiny made-up genome, where you've got 3 windows. You can see they overlap by about 50 base pairs. And then when you merge that, you just grab, I think, the average expression, the higher signal, and reduce the output. The thing that I really liked about the way I did this is you get the range returned, which you've got as the representative window, which then becomes easier for lots of visualizations later on. That's about it. I'm out of time. So hopefully that was a bit of a window into some useful utilities for those working with ChIP-seq or GRanges objects.
Oh, it is. Okay. Questions for Stevie? Got a roving mic up the back.
I should have been single cell, sorry guys. Right,
so am I getting your pun here? extraChIPs with GRAVI? Is this the...
Yeah.
Oh, I did. Good. Sorry.
Yeah.
There's some fabulous stickers up the back. So let's thank Stevie once again for a great presentation.
Oh no, there's a question.
Oh, good.
So yeah, that's really cool. I really love packages like this that just make a lot of things that you do routinely a lot easier. So obviously all the chip stuff's really cool and unique, but for a lot of the ranges operations, have you played with the plotHFGC package at all?
Yeah, absolutely. Yeah, and none of this duplicates anything there, but everything plays with it really nicely. In fact, the distinct came about from when I'm doing a lot of join overlap lefts. You end up with a lot of multiple mappings from range on the left to the one on the right. And so then just think you can kind of sort by whichever one you want to grab and then pull it out. So yeah, it was very much built because I was playing with plotRanges a lot. Yeah.